Okay, let's talk about blood pressure. Blood pressure is the hydrostatic pressure or the pushing pressure caused by the fluid inside our vessels. All vessels have blood pressure. We looked at that before when we were talking about venous return, and we discussed the pressure gradient that keeps the blood moving from high to low pressure and therefore always in the same direction back to the heart. Um, Despite the fact that all vessels have pressure, when we talk about blood pressure, we're typically only referring to the pressure in the arteries, in the systemic arteries. And the reason for this is that the pressure in the systemic arteries gives us information about how much blood is being delivered to the organs of the body, and therefore how much oxygen is being delivered to the organs of the body. Um, if we looked at the pressure in the veins, that wouldn't give us any information about our ability to serve the organs of the body. It would just tell us how much blood had already passed through. Um, so this gives us information about whether the heart and the vessels are doing their job to keep the body going. And pressure in the systemic arteries also gives us information about what kind of work the heart has to do. So the higher the pressure in the systemic arteries, the greater the work that the left ventricle has to do to get the blood into those arteries. We talked about this concept before in the heart chapter when, excuse me, when we talked about the concept of afterload. Recall that there are three factors that influence stroke volume, or how much blood the heart can pump out in any one contraction. Those were preload, contractility, and afterload. Well, afterload is what we're concerned about here, and that's why we look at blood pressure. Because if that pressure is high, that means that the afterload for the left ventricle is also high, and it's having to work harder to push its blood into the arteries because the pressure of the blood in the arteries is pushing back against it. So the reason we focus on the systemic arteries is because it gives us information about the heart and information about whether circulation is adequate to meet the needs of the body. Also, the pressure in the capillaries is very low and would be really hard to measure, considering how tiny those vessels are. And the pressure in the veins is so low that you can almost ignore it. So these don't give us a lot of valuable information other than just helping us to understand that there is a pressure gradient through the vessels that keeps blood moving in the proper direction. Now, blood pressure in the vessels is or changes with a number of things. As you can see by the fluctuations in this red line, the blood pressure in the vessels is affected by the contraction status of the heart. Each time the ventricles contract, the blood pressure in our systemic arteries goes up. As the ventricles relax, the pressure in our arteries, systemic arteries, goes down. So blood pressure changes with contraction status of the heart. It also changes as we move away from the heart, which is what we were just discussing. The further you get from the heart, the lower the pressure, and that's what keeps the blood moving away from the heart and eventually back to the heart. Blood pressure is also affected by blood volume. If you imagine yourself filling a balloon with just a little bit of water, there's not going to be a lot of pressure of that water on the balloon wall. But if you put more water into that balloon, it's going to stretch the wall more, which means there's more pressure inside. Blood volume is a very important component that we regulate, or that our bodies regulate, in order to maintain blood pressure. Blood pressure in our vessels is also affected by gravity, not just because it has to work against gravity, but because gravity influences how much weight the blood has on the vessels. Let me try to explain. The blood pressure in your feet is higher in the, let's say, the veins of your feet, for the sake of argument, is higher than the blood pressure in your abdomen. And that's because the deeper you go in the body, the more blood is sitting on top of you if you were a blood cell. Let's shrink ourselves down and become little scuba divers and see if it makes more sense. Many of you know that when people go scuba diving, the deeper they go, the higher the pressure under the water. And that's because the deeper a scuba diver goes, the more water is sitting on top of them and is sitting on top of the other water molecules around them. So if you were a little scuba diver and we put you in the jugular vein and asked you to swim all the way down to the feet, you would find that the pressure was increasing steadily as you moved downwards. This is why when we measure blood pressure, we also look for the pressure in the brachial artery because it's at the same level as the heart. If we measured your blood pressure in your legs, in your femoral artery, for instance, that would actually have an artificially higher pressure because of gravity. We wouldn't be comparing the pressure to the pressures that the heart is dealing with because of the weight of the blood on top of it. Now, going back to the fact that blood pressure changes with contraction status. As the ventricles contract and the pressure increases in the arteries, remember that contraction is called systole. We call this high pressure here systolic pressure. So it's the highest pressure in the systemic arteries and it's occurring with ventricular contraction. When the ventricles relax and the pressure drops in the arteries and the heart is in diastole, we call this diastolic pressure. And if we're measuring this at the level of the heart, at the brachial artery, then the pressure in the systemic arteries is usually about 120 over about 75 or 80. When they give you your blood pressure reading in the doctor's office, they'll say you have 120 over 75. That means your systolic is 120, your diastolic is 75. And that's how much the pressure fluctuates in your vessels. If they see, for instance, that the pressure fluctuates much more than that, or the systolic is too high, or the systolic is too low, or the diastolic is too high, or the diastolic is too low, this gives the clinicians the ability to diagnose issues that may be affecting the ability of your heart and vessels to get the blood around your body. Okay, now it's annoying to talk about two numbers all the time. So if I want to talk about blood pressure in the systemic arteries, I don't want to have to say, well, I'm talking about the systolic pressure now, or I'm talking about the diastolic pressure now. Or if I don't say at all, then nobody knows which one I'm talking about. It could be anything in here. So we use a tool or an estimate known as mean arterial pressure. The mean of something is its average. So we're looking at the average pressure in the arteries over time. So we're going to take the systolic pressure and the diastolic pressure, and we're going to put them together to get the average pressure in the systemic arteries over time, mean arterial pressure. We don't just average them. We don't take 120 and add it to 75 and divide by 2. That would be way too easy. In fact, we have to consider how long the heart is in systole and how long the heart is in diastole. At rest, in any one heartbeat, about a third of the time is spent in ventricular systole, and 2/3 of the time is spent in ventricular diastole. If you're exercising, diastole gets shorter so that your heart can beat faster. But we're just going to consider what happens when you're at rest. So at rest, 1/3 of each heartbeat is in contraction, 2/3 of each heartbeat is in relaxation. So to calculate or estimate mean arterial pressure, we say 1/3 of the systolic pressure plus 2/3 of the diastolic pressure. If we add those numbers together, that gives us the average pressure in the arteries over time and accounts for how much time we spend in each phase of the cycle, systole and diastole. So now let's talk about mean arterial pressure.